Hello and welcome back. Today we're going to start our last topic for this course, which is computation. And we'll be walking through a basic introduction to computation, computational models, the Church-Turing thesis, a halting problem, decidability, and things like that. And then at the very end, we're going to get into a little bit of reductions, P and the P versus NP problem. All right. So today, I'm going to introduce the topic here by giving you a motivating statement, or considering the following statement. All right. So algorithms, or if you really want to, you can go ahead and replace algorithms with computers. Right. Algorithms solve problems. Right. Now, on its surface, this is absolutely a correct statement. Right. But unfortunately, the statement falls short. The statement is plain old English, right? Right? Dictionary words with dictionary definitions, right? But computation is actually a branch of mathematics. Computer science is a branch of mathematics. It does not serve us well to simply pull definitions out of the dictionary. We have to actually have mathematically rigorous definitions in order to work with them. So what we need much more rigorous definitions and words in order to make the same statement, right? Now, intuitively, we understand that algorithms solve problems or computers solve problems. But when you really think about it, you can start asking more general questions like, do algorithms solve every problem? Right? Well, okay, what do you mean? Like, I lost my keys. Can a computer solve that? That's not. That's why we. That's why we need a rigorous mathematical definition. Because if you just simply use these, colloquial terms like problems, well, then people start to ask questions that are kind of irrelevant to what you were actually really originally talking about. Computer, of course, can't solve the problem unless you've got one of those Apple tags that you can put on stuff and then find what you're looking for. So I guess that is true. They can now solve your lost key problem. But what we're talking about is more given an input, can it produce an output? But to even begin to talk about that, we need much better definitions, much better terms for these things. And so what we have is the Church-Turing thesis. So Turing machines decide languages, right? Now, note here that I have translated each one of those three words into three direct terms here. Algorithms. What is an algorithm? Well, if you pull out the dictionary definition, it's a process for a step-by-step, well-defined process for computing something or whatever, right? What we need is a better mathematical term, and that's going to be Turing machines. Decide is going to be our solve. In other words, it's going to decide whether an input is in a language or not in a language. And that brings us to the last one. What is a problem? A problem is a language. Okay. So we're going to get to all three of these things eventually. But we have to start out with the most basic one first, and that's going to be languages. Let me go ahead and give myself some more room here while I am. I'll give you a reminder that we are on Piazza and YouTube if you have any questions. All right. So let sigma, this is sorry, there we go. Let sigma be a set containing 0 and 1, right? This is our alphabet. And it should look pretty familiar by this time. That is the binary alphabet, right? We're not talking about digits, decimals, 0 through 9. We're not talking about English, A through Z. We're gonna boil it down to just the essentials, 0 and 1, right? Binary. And we've already seen that we can do this, and here's a preview with Huffman coding. You can take a plain old English text and encode it, and you've got a bunch of binary. It was binary to begin with because of ASCII, right? You just compressed it, right? A string. Now, this is not necessarily like a Java string or a Python string, but it's basically the same idea. Or word, over sigma is a finite sequence of symbols from sigma. Right. Making sure that that's rendering correctly. There we go. So for example, if you want to typeset 0, right? 1, right? Those are words. But also 101, right? I can mash my keyboard here and come up with any binary string. And we do include binary strings with leading zeros. So those are still under consideration here. Not only that, but there's this very special symbol denoted by lambda. Right? Sometimes people use epsilon. I'll go ahead and use lambda, is the empty string. Right? And you can do this in Java, you can do this in Python. You just create a string with no characters in it. Its length is 0, and it's the special string called the empty string. It's not null. Null is a different concept. We're not going to have null or nil or none here. All right? So a set of all finite strings over sigma. These are not infinite sequences. You can talk about infinite sequences of binary, but that goes beyond what we're going to do here. A set of all finite strings over sigma is denoted as sigma star. There we go. That star operator is called the clean operator, and you might have seen that if you've ever seen regular expressions before. Match 0 or more occurrences of the following thing. Well, if you've got a set, you can say match 0 or more occurrences of anything in that set. And in this particular case, that means all finite strings. In fact, I'll go ahead and write them out here in lexicographic order. Lexicographic order here is going to end up being you order them first by their length. So, of course, the lambda comes first because it has a length of 0. Then 0, 1. And then you start counting in binary, making sure not to drop off those leading zeros. 0, 0, 0, 1, 1, 0, 1, 1, and then strings of length 3, 0, 0, 0, dot, 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 right? That's the set of all finite strings, right? And it's real. I mean, you've worked with them before, right? A computer is a finite object. It does not hold an infinite number of elements. In fact, you've seen this before when you've tried to do, say, 1/3. When you have a finite representation of a number, that's a rational number there. But when you have a finite representation, it's a 0.33333334 eventually. Other things like pi, which is an irrational number, or square root of 2, which is irrational. You can't even, you can only have a finite representation of those out to 16 digits or something. We're only talking about finite strings, finite sequences, okay? Therefore, what is a language? A language, over sigma, of course, is a subset of the a set of all strings. Sigma star. There we go. So it's just a subset of finite strings. Now, a language can be infinite self. A language may be finite or infinite, but the strings it contains are all finite. Okay? So that's what we're talking about here. So my claim is that languages are equivalent to problems. So again, consider something that we've looked at before. So an instance of a decision problem involves a configuration of data input as well as a yes or no question. So given a graph G, does it contain a cycle or not, or is it acyclic? Right? Given an integer x, is it prime or not, or composite? Right? You have the answer to those questions. Excuse me. The answer to those questions is yes or no. But how do you formulate the input itself? Right? When we write it out as pseudocode, of course, we've got these mathematical terms, and we've got these letters. G represents V, comma E, and that's a vertex set with V1 through Vn, and that's an edge set connecting those vertices, right? But at the end of the day, ultimately, you're going to be running this on a computer, right? And at the end of the day, what is a computer? It's nothing more than a bunch of binary, right? So all we need is a proper encoding. How does that network X Python graph actually get encoded into binary so that it can actually be run on my Mac or your Windows machine or whatever, right? It needs some sort of an encoding, right? Problems can be encoded as binary, right? And they all are, right? Everything that you can run in a computer is, of course, binary. Now, mathematically, the way that we express that is through languages. So here's G, a set of all graphs, G, such that G is an acyclic graph, right? If you define that language, that's equivalent to defining, or if you define that problem as a set, that's equivalent to defining it as a language, right? All you do is encode the input. So G, I'll encode that, and here's the special symbols that I'll use. Langle, wrangle. There we go. Give myself some more room here. G, right? Oops, sorry. That should be, there we go. Should be on the inside, right? That's that symbol, that's a special LaTeX symbol that we use to denote an encoding of G. And you've done this, right? Oh, you can encode a graph as a series of adjacency lists or an adjacency matrix. That adjacency matrix is just a bunch of zeros and ones, right? All you need to do is encode that it has n vertices, that it has, here are each one of these vertices. You did that with respect to your input values. You did it in a plain text file. Now that plain text file was over a different alphabet, right? The numbers, spaces, n-line characters, etc. But at the end of the day, it is encoded in ASCII, and that's one valid encoding. So I'm just going to denote that with this Langle-Wrangle symbol, okay? So now the question becomes, the question of, is G a cyclic, right? Cyclic, there we go. Now becomes, is G, the encoding of G, I'm just going to cut and paste this since I don't want to write the LaTeX again. There we go. In the language L, where now I'm going to redo that language up there. Oops. There we go. All encodings there we go, such that G is an acyclic cycle, right? Now I'm instead of talking about these abstract ideas of graphs and nodes and vertices and edges connecting those vertices, now I have an actual encoding. And so if I've got one particular encoding, X, then X is in the language if X validly encodes a graph, G, that contains no cycles. Right? It's not necessarily a tree because, of course, it could be a forest or something like that. And I did put in a caveat there, validly encodes. Of course, you could have bad encoding, as you've already experienced with your peers. Sometimes your peers are not too careful with the test cases that they submit, and they put UTF in there, or they skip a line, or something like that, right? So if we have an invalid encoding, we immediately throw that out, right? Otherwise, X is not in the language L. Right? So it all it boils down to decide a language is, given an encoding, is it in a language or not? Right? If it's in the language, in this particular case, then it encodes a valid graph that contains no cycles. If it's not in the language, then it's either invalid, and we can ignore those on both ends. We can check for validity first and say, nope, this is not a valid input. But if it is a valid input, then we can check it. If it's in the language, it contains no cycles. If it's not in the language, it does contain a cycle, right? You've also seen other types of problems. Other types of problems can also be encoded as a language. For example, optimization problems. Given a graph G, what does it have a Hamiltonian path, or what's the shortest length path from X to Y, right? And instead of outputting yes or no, what you can do is you can encode them, right? Instead of or to make the problem into a decision problem, that is a yes/no problem, you can always encode additional information. For example, I'll encode a graph, Langle, Wrangle, there we go. I'll encode a graph G along with two vertices, X and Y, and an integer K. Right? And I will say that this encodes, and the question becomes, is G a graph that that has a path from X to Y of length K? Right? And now it can be that optimization problem is now a decision problem. Because if I want to find the shortest path, what could I do? I could just ask for, well, is there repeatedly ask over and over again this language? All right, well, is there a path of length 1? Is there a path of length 2? Is there a path of length 3? Right? And the first time that it answers yes, then I can go ahead and stop and say, okay, well, the optimization problem has also been solved because I found the shortest path. You could work the other way and find the longest path to solve the Hamiltonian path problem by designing a different language, right? You can also have functional versions, right? Functional problems. Sorry, I am getting a new Mac finally with no butterfly keyboard. Right? Hopefully that will solve these typing problems. Anyway, functional problems, where suppose you know there is a shortest or longest path. You want to output the longest or that path. Right? What you can do is you can reformulate your encoding to be something like this, right? And I'll go ahead and go with Z, right? And there we go. And you can ask the question now, is G a graph with such that the shortest path contains an intermediate vertex Z? And then you can start asking this question over and over again of, okay, well, does it include that vertex? Does it include that vertex? Or you can formulate an even better version of this so that you can ask for, well, what's the next vertex? Is this the next vertex? Yes or no? Is this the next vertex? Yes or no? And then finally, you can build that path by simply asking that question over and over again from a decision version of the language. Okay? All right. So we now have a basis for which we can start talking about computational models, right? So to start out with, let's look at a very simple model called finite state automatons, right? And I don't want to write all this math, so I'm going to go ahead and cut and paste it. There we go. So an FSA, or finite state automaton, is a 5-tuple. Right? Just like a graph can be a 2-tuple, you can go ahead and group things together, and you've got a tuple here. Q is a set of it was a finite set of states. We're talking about a finite state machine. It can be in one state, and then it transitions to a different state. I'll show you a graphical representation here in a moment. But there are a finite number of states. Sigma is our alphabet, and again, for our purposes, we're going to be content with binary. Delta is a transition function. Given your current state and an input bit, 0 or 1, then we're going to transition to potentially a different state. We could transition into the same state. Q naught is a special initial state because, of course, we've got to start this algorithm somewhere. And then some of the states are accepting states. Other states are not accepting states. They're rejecting states. So just to understand what I'm talking about here, let's visualize this. All right? And we'll go over to the... All right, let's see. Where's my automaton? There we go. Here's an automaton. All right, here's a finite state automaton. You can see here that we have 1, 2, 3 states. We've specially marked this third state as an accepting state with this double kind of outlined circle. Otherwise, these two are rejecting states. Okay, let's go ahead and note that Q naught and Q1 are rejecting states. Every state is either accepting or rejecting. Q2 is accepting. All right. The transitions are shown as these arrows here. So here's the interpretation. Suppose that I'm in state Q1 here. Now I'm going to read the next bit of the input. If that bit is 0, I stay in that state. If that bit is 1, I move over to this state. Likewise, over here in Q2, I can either see a 0 or 1. If I see a 0, I'll transition back to this state. If I see a 1, I'll transition back to this state, which is also our initial state. Q naught is the initial state. All right? Now, the way that we accept an input string is whether or not, after all these transitions and we get to the end of reading the input, it ends up in an accepting state or a rejecting state. If it ends up in an accepting state, then we accept it and it's part of the language. If we end up in a rejecting state, we reject it and it's not part of the language. So let's go ahead and move this up here. And let's look at a couple of examples. So let's go ahead and go with 01101. Is that in the language or not? So we start reading bit by bit by bit. And on each bit that we read, we transition into another state. We start out in this state. Okay? So I'm here right now. I read a 0, which means that I transition over to this state. Right? Now I'm in this state and I read the second bit. It's a 1, so I transition over to this state. I'm in this state now and I read the third bit, which is a 1, and I transition back over here. I read the fourth bit, transitioning back over to this state, and then finally I read the last bit, which is a 1, and I transition over here. So in this particular case, yes, we do accept. What about some other examples? What about 0, 0, 0? So if I go 0, 0, 0, I start out in this initial state, go 0, 0, and then I go 0 again. And I end up in this rejecting state, meaning that this is not in the language defined by this finite state automaton. What about that special string lambda? Is that in the language or not? Well, if I start in the initial state here, right, there's nowhere to go because there's no bits to read, and so I would end up in a rejecting state, and no, it is not in the language. So just by looking at this, can you figure out what kind of strings this accepts and what kind of strings this rejects? To end up in this state here, I would have to have end in a 0, because a 1. But if I see a 1 after that, I go back over here. So how did I get all the way to this state to begin with? I would have had to see 0, 1. Then if I saw another 0, I would immediately get out of this. But I would still have seen a 0. If I see another 1, all right, 0, 1. If I see a 1, I go all the way back to the beginning, and I only get over to this accept state if I see another 0 and 1, and then I stop reading the input. Right? This accepts all strings that end with 0, 1. Now, there's another way of expressing that if you're familiar with, again, the clean star, or if you're familiar with regular expressions. Then any string, as long as it ends with a 0, 1, this is a regular expression. An equivalent regular expression for this machine up here. Right? And there is an equivalency between regular expressions and finite state automaton. Goes beyond this course, though, so don't worry about that. But otherwise, that's how a machine works. How a finite state machine works, excuse me. And the acceptance criteria that it defines this language is simply just, as I mentioned before, a finite state automaton, FSA, defines a language. Right? On input string X, it reads bit by bit and ends in some state. Right? And and transitions a state for each input bit. Ultimately, when the input is fully read, it ends in some state. If that state is accepting, the string is in the language defined by the finite state automaton. If that state is accepting, the string ends, or the string is not in the language. Right? So surprisingly, this is already a pretty powerful model. We can determine whether or not something is even or odd. Right? For example, if a binary string ends in a 1, then just a simple change of the machine that I just showed you. If it ends in 1, that means it's odd. If it ends in a 0, that means it's even, because as far as the binary representation goes. You can tell if it's divisible by 2. That's in fact the exact machine that we, well, I guess that's exactly what I just said. We can tell if it's divisible by 4. That's the machine that we just looked at. If it ends with a 1, 0, that means, scratch that. It just means that it's, I'd have to make absolutely sure for that one. But you can see that it's already a pretty powerful model, but it's not that powerful. All right, let's go ahead and transition back over here. And let's consider the language with n zeros followed by 1 ends. Right. So this is all strings that have an equal number, or that have, let me rewrite this. Start with n zeros and then have n ones. Right? So for example, 0, 1. Right? It has 1 0 and 1 1. 0 0 1 1. 0 0 0 1 1 1. Right? As long as you have an equal number of zeros followed by a number of ones for each n. For this is going to be for n being 1, for n being 2, n being 3, off to infinity. This is an infinitely sized language. It is it's seemingly very easy to compute. Some things that are not in the language, of course, would be 0, 1, 1, 0. Even though it has an equal number of zeros and an equal number of ones, it's not going to be in the language because it doesn't follow this pattern. All the zeros have to come first, and then all the ones have to come after it. Right? But it's a very, very simple language. But there's a theorem that says no finite state automaton defines this language. Right? This goes back to your first homework. We're not going to prove that theorem, by the way, but this goes back to your first homework, where we started talking about computational models, and you were asked to demonstrate that a stack was not as powerful as a queue. You could simulate a queue with 2 stacks, but I told you that the reverse, that you could simulate, a queue could simulate 1 stack, but you needed 2 stacks to simulate 1 queue. And that kind of showed that stacks have more computational power than queues. What this language is demonstrating, and again, we're not going to get into the proof here, but stacks have more computational power than not having a stack. Or here, let me rephrase that, because I don't want to say that we have 2 stacks, because then already you're up here, right? A stack has more computational power than no stack. Right? And let's go back over here to the finite state automaton here. We read this input bit by bit by bit by bit. We weren't allowed to go back and read and go back and forth and read this twice. It was a read once only kind of situation. And we didn't have any other memory. This is not like a computer where you've got memory and you can store stuff, you can write stuff to disk. You've got megs and gigs and terabytes of data storage to work with. We have no storage here whatsoever. A stack does have storage, and so it can provably do more. It can decide more languages. It can do more computations than not having a stack. How would you decide that language, by the way? 0n, 1 to the n. Here's an algorithm that uses a stack that decides this language, that decides given x is x of the form 0n, 1 to the n. Right? That's all we're talking about here. It's pretty easy. I'll write pseudocode for it. While the input bit, in fact, I'll go ahead and go with b sub I. I'll start I here at the start, right? Where if you wanted to go a little Indian, big Indian, doesn't matter. While b of I is 0, I will push 0 onto s. Right? Now, I've not counted the number of zeros directly. I've implicitly counted them. What I've done, say, for this particular example, 0001111, is I've created this stack, and I've pushed 0, 0, and 0. Now, while the stack... Well, once we first see that first one, then of course we jump out of this while loop. While the stack is not empty, or here, let me rephrase that. While b sub I is 1, right, we will pop from s. Right? Now at the end, so for this particular example, we will pop, pop, pop. And so we know that it's of this form if the stack is empty at the end, because we pushed just as many zeros as we popped ones. And so if the stack is empty, then accept. Otherwise, reject. We kind of like abusing the call stack. We abuse this stack in order to do our counting for us. And so it's arbitrarily big, but it's finite. We can push until we get to the ones area, and then we pop, 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 pop. Just to show you how it might work for something that we would reject. Right? 0, 0, 1, 1, 1. I will push 0, 0, and then I will transition to the second while loop. While it's 1, 1, 1, I will pop, pop, but then I jump out of that while loop, and the stack is not, or sorry, here's, okay, so I found an error with my pseudocode here. If the stack is empty and no more input, then accept. There we go. But here there is more input because there's an additional 1. So we'll end up rejecting it. What's another example? Suppose we had 0, 0, 1, 0, 1, 1. We would end up pushing 3 zeros, popping only 2 of them, and then we would end up rejecting because the stack is not empty. Right? What if it was something completely weird and different? It started with a 1, 0, 1, 0, or something like that. Right? Interleaved zeros and ones. Well, we would never end up executing this while loop, so our stack here would be empty. But while it's 1, I will pop from 0, and of course, there's a third case that may need to be incorporated into our pseudocode here, that if you ever tried to pop from an empty stack, you would end up rejecting. Right? So there are lots of details here, but you get the idea. A stack has more computational power than no stack, because here's one language that you can decide with a finite state automaton with a stack that you could not solve with a finite state automaton without a stack. Right? And if you have 2 stacks or you have a queue, you're even more powerful. In fact, you're as powerful as what's called a Turing machine at that point, which is the next thing we're going to look at. Right? So, well, let's talk about Turing machines now. And again, I'm going to cut and paste this because I don't want to write all the math again. There we go. There. So, a Turing machine, or TM for short, is a 7-tuple. So it's implicitly we have more. It's more complex. It's because it's more complex of a model, a computational model. Q is still a finite set of states. We can't have an infinite computer, but a computer has a finite set of states. It's just that it's really, really large, right? What did I just click on? I have no idea. This is CSCE 310. Hopefully you're a student. Otherwise, you just are rando on the internet. Anyway, sigma is still our input alphabet. This gamma is our output alphabet. That is gamma, right? Yeah, gamma. And they could be the same. In fact, they will be the same for most instances because of Huffman coding. If you have a set of symbols that is not binary, A through Z, you can always come up with a binary encoding of them. ASCII is another example. Right? There's a transition function here that is much more complex. Because not only are we reading the input, but we're also reading an output tape. Okay? And based on the current state, based on the input tape, based on the output that we can read and write from, we will transition to a new state, writing something on the output, and then either transitioning what's called our tape head left or right on the input and left or right on the output. Right? And we've got the initial state, of course. We've got ACC and REG, which are just short for accept and reject. Okay. Let's go ahead and take a look at a visualization of this. And I didn't pull it from my book, so I'm going to have to just recreate it here. I'll write it nicely, though. So this is the finite state control. It's looking at the input. I can write that nicer. All right, we'll do it like this. And there's some output tape. I don't want to write it so that it's closed, so I'll write it like this. Okay, and then I'll have to use my eraser to do that. All right, so here is the input. And there's some input x1, x2, x3, x4, ... and then xn. Right? Remember, that's just binary. And then effectively the tape ends there. And this is our output, or work tape. Right? A Turing machine now has memory, right, that you can actually write to and read from. This is read-only. But of course, you can consider alternative models where you are able to rewrite the input if you want to. They're equivalent because you could just take a copy of the input, put it down into the output tape, and then manipulate that if you really want to. The finite state control here is looking at some input value. It's looking at some output value over here on the output tape. I'll go ahead and go with y1, y2, y3, ... And generally, if you haven't written anything to the output tape yet, we use this special symbol to indicate blanks. It's an infinite read-write tape. Right? The idea here is that the finite state control is in some state. It's going to look at the input, so sigma here. It's going to look at what the current bit that it's currently reading, and it's also going to look at the current bit that it has written, or maybe it hasn't been written yet, and it's a blank space. Okay, and based on that, it's going to make a new transition to a new state. It could possibly stay in the same state, just like the finite state automaton, and it's going to write something to the output tape, potentially. It could say, well, I see a 0 over here, and I don't want to overwrite that, so I'll go ahead and write a 0 and then move on. And then it's going to move left, right, or stay the same on both the input tape and the output tape. Again, let me go ahead and annotate this. This is move the head. These are called tape heads, which are the bits that it's currently pointing to. Move the head left or right or stay. Right? I'm not going to move left or right. Right? I'll just stay put and continue looking at this bit over here. And this is squared over here because you have to do it for once for the input tape and once for the output tape. Okay. Now the idea here is that you have much more computational power here. The input is still read-only, but the output now is basically your memory. That's why we also call this a work tape here. You can read and write it. You can move back and forth. You can read and write as much as you want. And you can see here how we can take care of this language over here by simply just using the output tape here as our stack. If you want to, take this thing and turn it on end, and you get a stack. Right? Write a 0, write a 0, write a 0, write a 0, ... Until you get to until you get to 1, and then you can work the other way. Erase the 0, erase the 0, erase the 0, and rewrite it like it never happened. When you get to the end of the input, and one of those two conditions is true, or it's not empty, right? You got all the way back to the end of the tape, and there's no more input to read. Then you transition to this accepting state. Otherwise, you transition to this rejecting state. I've already written it up here. In fact, I'll pull it over, of what this machine would actually look like. Right? So let me jump to it visually first. Just bear with me here. I should have just... here, I'll start with this. So here's that finite state control that I redrew. Right? And here is the Turing machine that I just described. There. Whole bunch of different transitions, right? Now, I'm not showing you this so that we can go through it detail by detail. I'm showing this to you to show you that there is a hell of a lot of detail. A lot of detail that I don't want to deal with, right? This is kind of like the difference between writing in Python versus writing in assembly code, or writing, more accurately, writing directly in binary code. if you went back, 60, 70 years or whatever, and you actually had to physically, write stuff in binary by punching out a bunch of punch cards, right? That's basically what we're doing here. It's so low level that we have to come up with every single possible transition. And here is what the transition table would look like. Some of the transitions are not even possible. And so we immediately say we're not there. So if I start out in the first state here and I see a 0, and on the output tape I see a 0, well, that's an invalid transition. If I start out at the initial state, the input is 0, and I've not yet written anything, then what I'm going to do is I'm going to move my tape head, my input tape head right. I'm going to write write a hash, I guess in this case, instead of a 0 to the output tape, and then I'm going to transition over to Q1. Right? That's basically I didn't write it over here. Maybe that's a. We start here. Oh no, right here. We start at this transition, and then we would transition over here. So again, if we see a 0, it doesn't matter what's in the output tape. We'll write this special symbol hash to the output tape. We want and move right on the input tape. And then we continue to do that over and over and over again for as many zeros as we see. Once we see our first 1, we transition over to this, and that's basically taking out those ones. And we every time for every 1 that we see, we take that out, take that out, take that out. If we ever have one of those impossibilities, right? That you have you see a 1. But I forget which one each one of these corresponds to. But basically, if you've run out of input, but there's still stuff in your stack, if you have run out of stacks, you've erased everything out of the stack, but you still have input, then you immediately jump over here to this reject state. Otherwise, if there are an equal number of zeros, an equal number of ones, then you jump to this accept state. Again, I don't want to go through this in too much more detail with actual examples or anything like that. Instead, I just want to show you that writing Turing machine sucks, right? Just like writing binary code would really be terrible. Just like writing assembly is kind of really difficult, so some people actually like doing that. Instead, this is why we come up with pseudocode. Basically any pseudocode, any reasonable pseudocode that you can come up with, you can eventually design a Turing machine and get down to the low-level mathematical rigorous definition of all this stuff. All right. So that gives us the second piece of the statement that we started out with, that a Turing machine decides a language L if and only if it, 1, halts on all inputs and accepts or rejects if X is in the language or X is not in the language appropriately. There we go. So it'll end up in its accept state, just like this one ended up in an accept state if the input is in the language. It'll end up in this reject state if it's not in the language. The third condition there is that it has to halt. And you know from experience, everybody has written, either unintentionally or intentionally at some point, an infinite loop, right? You can have that with your algorithms. You can also have that with Turing machines. You can design a bad Turing machine that will simply just forget about the input, forget about the output. You're in one state, and regardless of what happens, I will just go ahead and stay in that state forever. Never going to an accept state, never going to a reject state. You're caught in an infinite loop, regardless of the input. The input will always be finite, but the computation of this Turing machine may end up taking an infinite amount of time. And time here is expressed in steps. It transitions from one state to another state. That's one step. It goes from that state to another state. That's one step. It may or may not be moving the tape heads and the input and the output, but it doesn't matter because a state transition is our measurement of time for a Turing machine. Okay, so it has to halt. So it has to be a valid Turing machine. Okay, so what we'll end with today is a question, and we'll answer it in one way, and then when we come back on Monday, we'll answer it another way. So, can computers, algorithms, / Turing machines, and just for some background here, Turing machines were named for Alan Turing, the guy who came up with the concept. Can computers, algorithms, Turing machines solve any problem? Right. Well, again, I'm going to throw out the dictionary definitions there. No, they cannot help you remember where your car keys were. Right? That's a person problem, not a computer problem. So what I'm going to do is I'm going to rephrase that. Can Turing machines decide any and all languages? Is there a problem that you can formulate in binary and ask the question, is it in the language or is it not in the language? And is there a Turing machine out there, an algorithm out there that can solve that problem? And the answer is a resounding no. Right? There are languages such that no Turing machine exists that decides them. There we go. Okay. I'm going to answer that question. So that was the answer, but I'm going to demonstrate the answer to that question here with what's called the diagonalization argument. So just to set this up, hopefully you've had this before, but say let's go ahead and go with Z. Right? This is the set of all integers. Right? 0 or -3, -2, -1, 0, 1, 2, 3, ... Right? It's infinite, but it is countable. It's countable because what I can do is I can take each one of these and I can put them in a one-way list. Right? Now, this is not in a one-way list right now. It's in a two-way infinite list. But I can go ahead and solve that problem by interleaving them. 0, 1, and then it's negation. 2, and then it's negation. 3, it's negation. ... Forever. What about Q? This is the set of all rationals. Right? Anything that can be expressed as A over B with B not being 0. Right? And A and B being integers. There we go. This is also infinite, and also countable. What it means to be countable is simply that you can put it in this list. You can put it into a one-to-one correspondence with the natural numbers. 0, 1, 2, 3, 4, 5, 6, ... You can count them and never miss one, and eventually it might take a very, very long time, but given a particular integer, you can say that it's in this list somewhere. Eventually you'll get to it. What about Q? Q is also infinite and countable. In other words, you can put them into a list, never miss one. You might end up repeating some, although there are these are called enumerations. There are enumerations that will never repeat anything. But you can come up with a list as well, right? So in other words, Z and Q have the same number of elements. Now that seems counterintuitive at first, and you're not alone. Darn it, now it's escaping my mind, but Cantor's diagonalization. When Cantor first showed this diagonalization, it was kind of rejected by a lot of mathematicians because it was for one of the first instances, or maybe the first instance, of a non-constructive proof. Not this part, but preliminarily, he wanted to come up with a notion of, well, what is infinity? Up to that point, infinity was infinity. Right? There is no differences in affinities. But he came along and pointed out that, no, actually, there are an infinite number of infinities. And each one of them is larger than the other infinities. Right? For example, R, the set of all reals, is infinite, but uncountable. Cantor showed that you can't enumerate them. You can't put all the real numbers into a line and not miss anything. You will necessarily miss something if you try to do that. And it was the first what's called a diagonalization proof today, because it simply just created this diagonal that I'll show you here in a second. But in other words, not all infinities are equal. In fact, he came up with symbols. Don't quote me on this because I don't know how to write it. Aleph. This is the Hebrew letter Aleph, right? Aleph. And this is null, the first one. That's infinity, right? Then there's Aleph 1, right? And this is the symbol that captures the infinitude of the real numbers. But you can continue. You can have Aleph k for any integer k, and there are an infinite number of them, right? The integers, the natural numbers, the rational numbers are all Aleph null, and the reals are Aleph 1. And then of course you can, the way that you can construct these is through like Dedekind cuts, or you can construct them using power sets, basically, right? We're not going to get into that. What I want to show you is that there are more languages than Turing machines. Right? All right, unfortunately we are slowing down here. There we go. Hopefully that speeds up. But in any case, there are more languages than Turing machines. The way that I'm going to show this is that Turing machines they're finite, they're infinite. They're an infinite number of Turing machines, but countable. Right? Languages are infinite, but uncountable. So just as there are more integer or more real numbers than there are integers, there are more languages than there are Turing machines. Right? And I'm going to show this by a proof by contradiction, which is also, again, it's basically the same proof that Cantor used to show that there are a different number of infinities. It's a diagonalization proof. Right? All right, so my first observation is that strings are finite strings countable. We already took care of this, right? Lambda 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, dot, 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 right? And now again, if you look at it as an integer representation, then we're missing negative numbers. This is not necessarily an integer, and of course we've got a lot of repetition here. 0 and 0, 0 are exactly the same representation, but whatever, right? The point is that they are countable. Okay? All right. I'm going to suppose, by way of contradiction, that languages. All right, here, and you know what? Let me back up. I'm also going to observe that Turing machines are countable. In other words, I can write out, here's a Turing machine. Here's the second Turing machine. Here's the third Turing machine, dot, dot, dot. Why? Because you can describe them in binary. Remember, a Turing machine is just an algorithm. You write some code, you compile it, and ultimately that's just a bunch of zeros and ones, right? It's a bunch of machine code. Likewise, over the tables that we put together, those can be encoded in binary, and now you've got a binary representation of Turing machines. In other words, you can put them in a in lexicographic order, just like we did with strings. Right? My claim is that languages are not countable. Right? In other words, that that there are an infinite, there are provably more languages than there are Turing machines to decide them. And my proof here is by contradiction. By contradiction, or by way of contradiction, suppose languages are countable. Again, are countable, right? Furthermore, you can suppose that they're in the same order as the Turing machines. That the language that I'll write it up here, L1, L2, L3. We'll just assume that this Turing machine decides this language, this Turing machine decides this language, this Turing machine decides this language, dot dot dot, all the way over to infinity. Right? By assuming that its languages are countable, I can go ahead and put them into this enumeration that matches up with my Turing machines. This is the non-constructive part. I don't know how to do that, right? In fact, no, you can't do that, because ultimately we're going to come up with a contradiction where you can't line up all these languages up in a row because they're not countable. But we're supposing by way of contradiction that you can. Now what I'm going to do is I'm going to write out this really large matrix. So 0, 1, 0, 0, 0, 1, this table basically. 1, 0, 1, 1, dot, dot, dot. In other words, these are going to be strings. Remember, I can do this because they are countable. By way of contradiction, I supposed that I could do the same thing with the languages. M1, right? This is abusive notation here. The first machine and its language, I can write that out. M2, L2, M3, L3, dot, 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 MI, LI. And suppose I can do the same thing over here. I'll just call it X of I. Okay? Now, this is an infinite. This goes on for infinity, right? But there are going to be entries here. So these entries are going to be zeros or ones. And here's the interpretation. So this entry is going to be 0 if here, let me rewrite it. Entries X, Y, I, J, right, is equal to 0 or 1. It's equal to 0 if X of J is in language else of I. All right, so again, X of J, this column, jth column, ith row, is either going to be 0 or 1. It's 0 if this string is in this language. It's going to be 1, or sorry, if it's not in the language. It's going to be 1 if it is. Doesn't matter, go ahead and swap them if you want. Right? So 1, 0, 1, 0, well, I'm just making this stuff up, right? Again, I'm not even able to do this in real life, because we're going to hit a proof by contradiction eventually. All right? Now what I'm going to do is I'm going to construct, and dot, 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 everywhere, dot, 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 construct a new language. And the way that I'm going to do that is by diagonalizing. So look along the diagonal here. Right? What I'm going to do is I'm going to intentionally disagree with it. So this new language L will be all X of J such that X of J is not, let me go ahead and go with I here. X sub I such that machine I rejects X of I. There we go. In other words, if it rejects, I'll accept. So basically what I'm doing with all these zeros, I'm flipping them over to 1, 1, 1. If there's a 1, I'm flipping that to 0. Right? Now my observation here is that no machine decides L. Why? It disagrees with L sub I in whether or not X sub I is in L sub I, right? Again, observe here. If X sub I is in L sub I, if and only if, by the definition that I just created up here, if and only if X sub I is not in L. And likewise, by exclusion here, X sub I is not in L sub I, if and only if X sub I is in that other language. So in other words, L is not equal to any L sub I for any I. So I've come up with a language here that no machine decides. Right? And I've done it non-constructively. In fact, there are an infinite number of more of them. I've done it non-constructively in the sense that, which language is it? What is L? I don't know. Is it a language that corresponds to a problem about graphs? Is it a language that corresponds to problems about prime numbers, right? I don't know. I didn't construct it, right? But when we come back on Monday, we will construct a language that has actually very practical use. Given a Turing machine and an input X, does that Turing machine eventually halt, or does it get stuck in an infinite loop? That'd be great if a compiler could tell you at compile time, nope, there's this input out there that it's not going to work on because it's going to get caught in an infinite loop here, or that it's going to take more time than you have to do this or whatever. Basically, all those practical questions can be proven to be impossible. Right now, there are some ways that you can do this with static analysis and stuff for small programs and simple programs. But the proof is that this is called the halting problem. Does this algorithm halt? Does this Turing machine halt on all inputs? No, there's no Turing machine that can actually decide that. Right? So that problem is not solvable by any computer or any algorithm. Right? There are lots of languages and problems like that. Okay. So have a good weekend. Make sure that you're getting a good start on the final homework. Since we've covered dynamic programming completely now, of course, the programming portions, you should be able to get started on those right away. Have a good weekend.